So then we can start, and if somebody here is an expert in general relativity, actually there is no need for you to waste your time. On the other hand, if you are not an expert in general relativity, then this is really a very, very essential lecture for the discussion of accretion disks. This is just the basic thing. So we will talk specifically, not yet about accretion disks, but about the motion of test particles in gravitational field of a black hole. So first, you must know something about general relativity. So usually there are various courses like skiing in weekend, whatever. So I suggest even more advancing, like course of general relativity in 15 minutes. And I hope this will work. Fortunately, we will not need full general relativity when studying accretion disks, but we need some key statements from that. So general relativity, as you know, was introduced by Albert Einstein already in 1915. And at the beginning, this theory was not broadly applicable. The motivation was mostly theoretical. Why he developed that? At that moment in 1915, there were two possible, two possible effects which could allow to test general relativity. That was light bending close to the sun, and the second was precession of the Mercury orbit. This is quite amazing that in astronomy, precision of measurements was always very, very large. Well, the precession of Mercury orbit, of course, is this effect that, well, the orbit is elliptical, and then it's the position of the maximum changes. And most of the effect is actually caused by other stars. So the effect of precession would be 500 arc seconds per century if there is no GR or anything like that. And it's mostly other planets, actually Jupiter is mostly responsible for that. But nevertheless, there was a problem of 40, more or less 40 arc seconds per century, which was missing. And general relativity accounted precisely for that. This is the total budget, which was determined in 47, but I think the precision was not much worse during the Einstein epoch. Now it's probably much, much higher, but I didn't find the latest value. Probably nobody bothered to keep that. Anyway, it was really a very impressive theory, but if you look at citations, this is not really the most cited paper of Einstein. As you see, the leading paper is almost 7,000 citations so far, is Einstein-Podolsky-Rosen, 35, on a different topic. And the effect is because everybody who uses GR does not cite Einstein, right? Okay, nowadays, of course, we need GR, and we need it in astronomy. And when we look at the image of M87 from Event Horizon Telescope, we need to understand black holes to appreciate this hole, which is here inside. But we need it in everyday life as well, because GPS has all full GR corrections, and they are essential. Without those, you would be lost. As simple as that. So now this course of general relativity. So the essence of general relativity is that there is no force like gravity, but everything is coded in the curvature of space. Space is curved, and this is the reason why all bodies move in the same way in gravitational field. So because we will talk about geometry, we have to introduce the way how we measure distances, right? And in the classical mechanics, we measure, oops. Wrong direction. Now I'm going properly, yes. In classical mechanics, time intervals are constant, the same for all observers. If you change an observer, this does not change. And you have to only measure the distances in space, and then you have to use proper coordinates, but in Cartesian coordinates, the expression for the distance is like that, and this distance does not depend on coordinates. But of course, this part of the expression, yes, it does depend on coordinates. In special relativity, the situation is already more complicated because time and space are mixed. So then here we had independently that always dt is constant and the spatial distance is constant independently from an observer. But in special relativity, we have space-time interval, which is defined in this way, in Cartesian coordinates. And only this part is constant. So the time interval can change and the space interval can change if you change coordinate system, if you change reference frame. On the other hand, this quantity is preserved. Now we used Cartesian coordinates, but we also can use spherical coordinates, and we will use spherical coordinates in most of the next lecture. So spherical coordinates look like that. If you want to use them in classical mechanics, you also should calculate the distance using this kind of expression. I guess you know that. Of course, here c is the light speed. So in the case of special relativity, time and space can be modified if we modify coordinates, but the effect of mixing is time and of time and space is only important when velocities are very high. If velocities are small, then we have classical situation. So since this space-time interval is really absolute, then we have to look at it more closely. And you see that it contains two factors. And in principle, if, for example, something is in rest, then this would be positive. But if, for example, we measure distance, let's say in the same time moment between 2 points, then this would be sort of 0 and this would be negative. So this ds square can be positive or negative, right? It's a customary thing, so don't bother that everything is imaginary or something like that, although some people really like to use imaginary values for time, for example. Anyway, then you see that if the s square is larger than 0, you have time-like intervals. And if this is less than 0, you have space-like intervals. And of course, at the border, you have this equals 0. And this describes the propagation of photon, right? For photon, the distance, the space-time distance is zero, but still it propagates. And this is also very important for the organization of events, because in absolute, when we had absolute time in classical situation, then what happened later or earlier, then it was quite clear. But if you have a mixing, then in some coordinates, for some observers, one phenomenon can be earlier, the other can be later. For another observer, it can be the opposite. However, it's not always arbitrary. So for when points can be connected with the word line, so this Diaz square is larger than zero, then events can be ordered using light or using test particle, which will organize them. On the other hand, if this is negative, then you cannot tell in any absolute terms what was earlier, what was later. Those are just spatially separated events, and you don't know what happened first. Now, if we go to general relativity, things look more or less the same, only mathematically they become much more complicated, because here, if you use Cartesian coordinates, those coefficients are very simple. If you use general relativity, you never find coordinates where things look simple. So you have here coefficients in front of this kind of thing. So you can imagine that, well, if you go back, for example, we can go back to this. So in the case of spherical coordinates, this also happened, right? You had the theta and there was something in front because of the coordinates. So now the only difference between this situation and spherical coordinates and full GR is that it's always like this. You have always something in front. And the customary notation is that if you have index, lower index and upper index, you should perform, excuse me, you should perform a summation. So actually this is a long expression like this with a number of terms like dx squared, the y squared, but also dx, dy, dt, dx, all combinations in principle. So all geometry, all information of geometry is now coded in this tensor metric. So this tensor metric, according to Einstein, is determined by the material which fills the space. Because if there is no material filling the space, you have empty space and everything reduces to special relativity, no problem. But if you have some material, then you have to determine this metric tensor. And original equations had this form, where on the left-hand side you had a tensor which contains this metric tensor, its first derivatives and second derivatives. So this is second order equation, a set of equations actually. And here there is a tensor, an energy tensor, stress energy tensor, which contains not the information about mass, but also pressure, stress forces, because everything affects the gravitational field, right? You have equivalence between mass and energy. So any form of energy acts like mass and then affects the gravitational field. So recently, or actually it was Einstein who introduced cosmological constant. Because in principle, you can introduce this. Equations look more or less like that, and then instead of this complex things, you have just alpha times the metric tensor. And recently, most people move this cosmological constant or this part to the right-hand side of equation, and then you have various models of dark energy. But in the rest of the lecture, we will not talk about cosmological constant, because we are interested in just black holes, local description of black holes. So we can forget about those terms. So we will use only this part. So as I said, if this tensor is zero everywhere, not just at one place, but everywhere in the space, you have flat space. But if it is non-zero, at least in one place, even if you have a point-like source, then you have to solve those equations. Of course, those equations are very, very, very difficult. So in general, you do it numerically nowadays. And there is very nice software named Einstein Toolkit. So if you want to solve full GR equations with sources, then you can use it, for example, to calculate coalescence of black holes or anything of that sort. On the other hand, we will concentrate only on those cases which are simple and can be, excuse me, I'm evidently developing a code, which are simple, and then a solution can be found analytically under certain assumptions. So the first case is cosmology, where you can assume that the universe is uniform and isotropic, and that simplifies the thing considerably. Typical equation which is used then is now called Friedmann, Lemert, Robertson, Walker, whatever. It was really found first by Alexander Friedmann. In English, he's written with double N for some reason, I don't know why, or in original, it's written with, if you can read Russian, with single N, and in Polish, it's with single N. Anyway. He published everything in 1922, and then next paper in 1924. It was published in German, so it was accessible to the guys who published the solution later. So I really don't know why they are hanging here. I think it should be just Friedmann. Solution. That's, you know, there are local patriotics, and anyway, this solution looks like that. So it is relatively simple. Here you have the same space-time. Distance, time term looks simple. On the other hand, this is almost like spherical coordinates, but there is this problem and this problem. So this thing which is in front, this is just a scale factor which describes the expansion of the universe. And this is what we see in observations. On the other hand, here, this is more problematic term. But if k is equal 0, then this part looks exactly like spherical coordinates before. So that means that the space is flat. And actually, currently, our universe looks like it's flat. And the whole cosmology is, and GR effect is just due to this expansion term, which is in front. On the other hand, in principle, the universe does not have to be flat. It can be curved, so this k factor can be positive or negative, and I did an exercise. Namely, if you calculate the radius of, because spherical coordinates here, this part tells you that if you calculate the circle, then the length of the circle is 2 pi r. This is what you have in spherical coordinates. So because you didn't touch spherical coordinates, you will have 2 pi r, the length of the circle. On the other hand, if you calculate the radius, then you should, if you have the r, then if you integrate the r, you have r. But if you integrate the r, but that part including, then the radius is different. And you see that depending on k, whether it's positive or negative, this radius can be larger or smaller, corresponding to the curvature, which you can imagine as closed or negative curvature, or you have somehow more space. So currently, universe seems flat. So for the universe, this is not so important. But now we are going to the black hole solution. And this is of interest. And there, this effect will be important. So this is the solution for a non-rotating black hole. This is a solution which is parameterized only by one parameter, value of the mass, m. So the assumption was that we have a point-like source of a mass m and zero angular momentum. We'll later mention the case of angular momentum, so this is why I stress this. But this solution was found by Carl Schwarzschild in 1915. So in the same year as full GR was published. He was quite fast, even then, you know, some people were really quite fast. It's really unfortunate that he died a year later. So he had no chance to contribute more to general relativity. So here in this solution, you see Schwarzschild radius, which was introduced already during the first lecture. And this Schwarzschild radius appears in two places. It modifies the time term and modifies the radial distance, while this part in spherical coordinates, this remains as usually. So the length of the circle will be still 2 pi r in that case, but the radius of the circle will be different. So this solution assumes spherical symmetry, of course, because if you have a point-like source, but actually it applies to a broad range of situations, because if you have a star which is spherically symmetric, larger than Schwarzschild radius, for example, still outside the star you apply this solution if you want full GR solution. But then inside the star, you have to find another solution, because this corresponds to locally empty space, right? So inside the star, you have to find another solution, which will depend on equation of state, on properties, cooling, whatever. You have to know everything about the star, and you solve this. So now for those who are not really familiar with black holes, a short digression about the origin of the concept. So origin is quite really old, because John Mitchell, that was the first one, he considered the problem of so-called dark stars already in 1783. He gave a talk At that time, they did not yet publish things. They gave talks, right? He gave a talk and he proposed his thing. But I think there is also a written version of Aya. By the way, I saw recently in the internet that some people publish this portrait in that context, and that's a mistake, because this is again John Mitchell, but not John Mitchell. That lived 100 years later, and that was an Irish nationalist, activist, solicitor, whatever. It's not that one. For that one, we don't have any image. So, but it's still not justified to confuse people, right? We don't know how he looked like. I think he was a clergyman anyway, Reverend John Mitchell. So what he considered an escape velocity from a body, from a star of a radius r and mass m. And he started to think, what if the radius is so small or the mass is so large, then the escape velocity is equal to the light velocity. In that case, the light will not escape, right? If light does not escape, then we will not see this star. And then he introduced this concept of dark stars. And he calculated the situation. So the energy is, in general, kinetic energy and potential energy, Newtonian mechanics. And if you have put it set to 0, you calculate the escape velocity. And then if you put escape velocity equals c, you can calculate the radius of the dark star. And this is again the Schwarzschild radius. So he did it really many years ago. So it gives properly, so Newtonian physics gives properly the value of the radius, Schwarzschild radius, but it does not represent properly the motion of the photon close to horizon, and we will return to that moment also in a minute. So in order to illustrate how this modification of gravity changes the situation, changes what is happening close to the black hole horizon. We are not going now below the black hole horizon. Locally, you can always introduce coordinates which are locally at that point Cartesian. So in that case, you would have a new time coordinate and new space coordinate. So if you introduce new time coordinate, then for such coordinate, if radius is very close to the Schwarzschild radius, the d tau is almost 0, right? The time is not flowing close to the horizon. On the other hand, for space, this now goes to 0, and this almost goes to infinity when r approaches Schwarzschild radius. So we see that there is much more space in a sense. So sometimes people draw it schematically like this. Let's imagine that in the case of flat two-dimensional space, we draw circles like that. But if we have two-dimensional but curved space, those circles go inside deeper and deeper. So then 2 pi r is as here, but the radial distance approaches infinity, right?
Sorry, will that c be there in d tau, and the dt should be outside the square root?
Ah, yes, it should be outside, of course. Yes, my mistake. Yes. Yes, it should be outside because it is just the square root of this, because we replace this with d tau. So you are perfectly right.
But do we include the c or not?
Oh, we include again, you are right. No, we shouldn't. We shouldn't, because otherwise you would have problems with dimensions, right? Of course, if people use C equal 1, then it's not a problem, but I usually don't use. So you are perfectly right. Sorry for that. So here we can also represent, in a sense, the velocity using those new coordinates. And then this velocity, which is observed by a distant observer, is related to the local velocity for this special observer by this factor. So then from the point of view of the distant observer, if something is falling onto the black hole, it falls slower and slower and slower, and it kind of freezes at the horizon. On the other hand, locally, it's not true that the infalling particle is flowing faster and faster and faster and reaches the light speed at the horizon. So once more here, the difference between this old picture of Mitchell and actually the picture of general relativity. Because what you see here is that if you try to be inside the Schwarzschild radius, then this part becomes negative, right? And this also becomes negative. So in a sense, this term, which was positive, becomes now negative, and this time, which was negative, becomes positive. So in a sense, time and space change. So time inside the horizon plays the form of space, and inside the horizon, only motion inside is possible. So if you are inside a black hole, you can actually move back or forwards in time, it does not matter. But your fate is anyway determined because you have to move towards the central point, which is r equals 0, and which is really singularity, and you will die there in a finite time. So this sort of determines that now in full GR inside there is geometry working, which I would imagine like moving train, which moves with speed larger than light speed. Because if you are in the train, you cannot, whenever you go forwards or backwards, you move with the train, right? So there you have a sort of a train which is faster than light, in a sense. And this makes the difference between this old Newtonian concept of Mitchell for a photon at the horizon, because Mitchell imagined that photon emitted here will try to escape, will reach some maximum point, and then it will return. But in the case of GR, this does not happen, because this space is dragging the photon. So if photon is emitted in this way, still it will fall towards the center. And if it is emitted here, for example, there are two photons emitted at the horizon, one emitted in this direction and one towards the center, that one towards the center will fall immediately towards the center. But that one emitted outward will be just standing there like a mouse, you know, like trying to fight the gravity, but not getting out. So it will stay there. It will not go out. So that's the difference in deeper understanding of the situation at the horizon between full GR and the Newtonian approximation. So that was the course of full GR. Now we go back to Newtonian theory, but now we need some material about equations of motion, how we solve the equation of motion. So this we already had before. This is the Eulerian equation. Now we are interested in test particles, so we drop the pressure, but we keep the gravitational force. And gravitational force is known as conservative force. And any conservative force can be represented as a gradient of the potential. So for example, frictional forces, they cannot be represented like that. But you know, gravitational potential, this is really a well-known concept. So now the equation reduces to this one. And it's quite easy to show how from this equation you obtain the conservation of energy, because this is a very convenient thing. Instead of solving all equations, if you have the conservation of energy, everything becomes simpler. So then, because of the potential on those properties which we discussed here, if you calculate the full time derivative, you have only this velocity part, but this you have no explicit dependence of gravity on time. We assume that because matter cannot be created or annihilated or whatever. And then you can combine those equations. You first multiply this equation by vector velocity. You get this, and then you can integrate this already. Because from that part to that part, you go really easily. And you determine the conservation of energy. So this total energy consists of gravitational potential and kinetic energy, and this is per unit mass of a particle. In the same way, you can determine the conservation of angular momentum. You start with the same equation, but instead of multiplying by v, you multiply by r. This is the vector multiplication. And then you have to work out, then we have to assume that, well, the potential is spherically symmetric. In that case, additional things vanish. And then you can determine the angular momentum conservation. So this was the scalar thing. This is the vector. But in the case of Newtonian gravity, I think you all know that the motion of the particle happens always in a single plane. So then you can refer to this particular plane, to this special orbit, and then instead of vectors, you consider just conservation of angular momentum for the value and energy. So here we have radial velocity, here we have phi velocity, because I assume that we are using spherically symmetric coordinates, and we are in the equatorial plane, so theta is equal pi half. So those two equations are, I guess, are really well known to you. In general, they still describe quite complicated motion. Those orbits are so-called equivalent to oops. Okay. Oh, reset this. I'm not sure what happened. And then I don't know how to go back to this, to the standard value.
Try to double click. And once again.
Oh, yes, yeah. Yes. Oh, okay. Thank you, Arthur. Okay, so we have those conic sections. So in general, orbits can be elliptic or parabola or hyperbola, depending on eccentricity. But we will be really interested in circular orbits. Let's make everything simple. So now how to get the condition for the circular orbit. We have this equation of energy, and we have the equation of also conservation of angular momentum. So to get the circular orbit, radial velocity should be 0, but that's not enough because in one point of elliptical orbit, radial velocity is also 0. So we have to be more consequent. We have to assume that the derivative of the radial velocity is also 0. So here I still kept this general potential. But we see here that we here have a term with velocity, and here we have term with angular momentum. So it's more convenient to include this part into gravitational potential. So we define now effective potential. And in the Newtonian case, this is minus gm over r plus this angular momentum term. So now putting this into that, we can use those two conditions. And after calculating, differentiating properly 2 times everything, we get that the angular momentum on a circular orbit is equal square root of gm over times r. And we can also calculate the energy. We were using it, by the way, already a couple of times because I assume that you know that. And we know what happens to how to get the circular orbit. So this is once more the summary, the angular momentum, energy, and this is the shape of the potential. So the circular orbit is determined by the minimum on this potential. And indeed, now it looks like 2 simple things why we are doing this kind of exercise, but now we are doing something a bit more advanced. We try to cheat and do full GR, not using GR equations. And the method was invented in 1980 by Bogdan Paczyński and Paul Vita. They, instead of minus gm over r, they introduced pseudo-Newtonian potential to imitate the position of the horizon. And in the same way, we can define this effective pseudo-Newtonian potential. We have this part, and then we have this part connected with angular momentum. And now we repeat the same exercise. We differentiate to find circular orbits. And this is really the key of the lecture. This is the most important part of the whole lecture. What happens? Now everything changed. Because the equation became more complicated. So on one hand, for a given radius, you can calculate the Keplerian angular momentum, But if you want to reverse the problem, namely for a given angular momentum, you want to calculate the radius of the orbit. It's not just one orbit, there are two orbits. So this is the shape of the Keplerian now angular momentum. In the Newtonian case, it was like this. It was monotonic function. So you had always one solution. Now you have two solutions. And on the potential, it looks like this. Instead of potential like that, you have this, and then it goes down when we approach Schwarzschild radius. And then you have two minima. Here is minimum, and that intuitively shows you this is a stable situation, right? Because you are in a minimum. And then here you have a maximum, because you, and this is not stable because you are sitting on the top of a hill, right? So any perturbation which will push you from this circular orbit as either inside or outside, whatever, but it will not be stable. And what is happening depends on the angular momentum, because the previous picture was drawn for some angular momentum, right? So now if you change this angular momentum, I started with a rather large value, you had this kind of shape, but then you decrease the angular momentum decrease. So then one solution is here, the other solution is here, and the two solutions approach. And finally, for one particular value of the angular momentum, there is just one solution, which is neither stable nor unstable. This is marginally stable orbit. And this is really the most important concept which we'll be using all the time when doing calculations of spectra, of everything. And from these equations, solving those equations, it's easy to show that this marginally stable orbit is equal 3 times Schwarzschild radius. And sometimes it is called marginally stable orbit, or recently more frequently as innermost stable circular orbit, shortly ISCO, and that should be easy to remember, right? You know that guy, or at least some of you can know this guy. Well, he's a player of which? It's the same name. I mean. So why this is really important? Because now we know that if we have an accretion disk, then we have a sequence of circular orbits, and they are stable. So you have to subtract angular momentum to allow the particle to move onto closer orbit. And you repeat that, but then you approach finally marginally stable orbit. And then you don't have to extract any more angular momentum. The particle just by itself will flow onto the black hole. So this is the end of the extraction of energy, because angular momentum has to be extracted, but also to remain on the circular orbit, you have to extract the energy to be consequently on a circular orbit. So if you calculate the energy at this marginally stable orbit, or ISCO orbit, then you will determine really the efficiency of the accretion, because further accretion will not require any loss of energy, any loss of angular momentum. And this is a major difference between spherical accretion and disk accretion. In spherical accretion, I told you it's very difficult to estimate the efficiency of accretion. Here, you can estimate the efficiency of accretion as 1/16, Independently, I didn't say anything about this temperature, density, whatever. It's just Keplerian circular orbits, and that's enough, and you can calculate the efficiency of accretion.
Excuse me.
Yes.
I'm not getting one thing. So instead of working with GR, we use this pseudo-Newtonian potential. Yes. What is its good property?
Well, it gives properly the marginally stable orbit, the position. It's consistent with Schwarzschild solution non-rotating black hole.
But given the same angular momentum, what?
Well, given consistent, yes. Well, the marginally stable orbit does not depend on angular momentum. This is for specific angular momentum, right? Mm-hmm. Because angular momentum sets you the orbit radius.
Okay.
So then, if you have marginally stable orbit or this ISCO, you have this angular momentum, and actually this angular momentum is equal this.
No, because in GR we also change the way in which we compute angular momentum and the energy.
Yes, yes. So I will mention that. So if we go back to Bondi flow, I mentioned to you that in Newtonian.
I have one question. Like below the marginal, below the ISCO radius, we don't extract any energy. Like,
no, you have free fall.
Yeah. So. But
you had to extract the energy to get here.
There is also the possibility, like if the particle is charged, it can also emit from the Bremsstrahlung because it's going through the quasi-circular.
Well, we are not talking about emissivity. We are talking about test particles. Okay. Test particles are never charged by definition, right? So if we consider Bondi flow and Newtonian physics, you always have some angular momentum barrier if the body is compact. But here, this is the next difference between pseudo-Newtonian and Newtonian case. If you have a low angular momentum below this value, then you will see no angular momentum barrier. You will have spherical flow, practically spherical flow. Okay, so now we go to Schwarzschild radius, Schwarzschild solution. And in that case, in principle, you should solve this kind of equations. This is for just full GR set of equations. But for Schwarzschild metric, you can put all those conservation laws inside. So you still have energy conservation and angular momentum conservation. And the structure of the equation is similar. You have here velocity, and here you have energy term, and here something which is related to radius and angular momentum. So you can introduce to some extent Schwarzschild potential like this. And you see that it's not really the same like in a pseudo-Newtonian case. So this is exact solution. This is not cheating. And here you don't have this R minus R in R Schwarzschild in denominator. This is like in Newtonian case. On the other hand, here you have a term which somehow suppresses the centrifugal force. But indeed, the net effect is the same. If you calculate, you will have again two solutions for the Keplerian orbits, stable and unstable family, and the marginally stable orbit will be exactly the same, 3 Schwarzschild radii. On the other hand, the prescription for energy will be somewhat different, and then the efficiency is also somewhat different. It's not like in pseudo-Newtonian case, but it's not that much different, right? But in principle, black holes can rotate. In Newtonian physics, if you have a point-like source, There is no way to say that point-like source rotates, has angular momentum, and changes gravity around it. On the other hand, in general relativity, this rotating thing changes the gravity. And to find a solution for a point-like source, but with angular momentum, which has only axial symmetry, not spherical symmetry, that was much, much more complicated. So the appropriate solution was found only in 1963 by Reuker, and that guy is also frequently not cited because, you know, it's kind of too obvious. You use Kerr metric and who cares where it was published. Excuse me. So now the solution is much more complicated. You see that? The angular momentum here is represented by dimensional parameter A. A square is smaller than 1, and A varies between -1 and 1, which one positive means that orbits, we consider orbits co-rotating with the black hole, and if it is -1, it means that we fix the direction of the orbit, but the black hole is counter-rotating. So now everything is much more complicated. Actually, the motion now is not always in one plane. You can have motions with changing planes. You can have particles levitating there or something like that, which is not possible in Newtonian case. But we will constrain ourselves only to the equatorial plane because that's complicated enough. You see, this is the equation only in the equatorial plane. It's much longer. And the additional effect which is seen in the equatorial plane is that if you try to fall towards a black hole with zero angular momentum, you might think that you will fall like this, but it's not true. The black hole is dragging the space, so you are dragged in this direction, in the direction of the rotation. And this dragging is very strong. So at some point you have this ergosphere region, which is even before you reach the horizon. And there the dragging is so strong that you cannot really move in the opposite direction. Because here, if you insist that you have some angular momentum, you can try to go around it. But in ergosphere, it's like under horizon. In under horizon, you have to go towards the center. In ergosphere, you have to go this way or that way, but you have to go along the direction of the rotation. You cannot be counter-rotating. And in that case, the situation of orbits is also very, very similar. You have also marginally stable orbit and two families of the orbits, stable and unstable. So mathematics is much more complicated, but conceptually, everything is basically the same. So this is why this pseudo-Newtonian thing is very useful, because it helps you to understand how this works. But of course, the position now of this ISCO or marginally stable orbit depends on the angular momentum.
Could you please tell me what does dragging mean over here?
Dragging means, well, because the central black hole is rotating, so the whole space is somehow moved. Like when you have Newtonian gravity, you would know what is dragging you towards the center, right? It is a kind of gravity. But here there is this rotational motion, and it drags you in the same way. You cannot do anything about it. I don't know how to invent any other word for that dragging.
Is it the metric which is get dragged?
Yes. Well, metrics describes the phenomenon, right?
is there a point where this metric, like let's say if we consider it's like an elastic material, it breaks? Is it possible?
No, no, it does not break. The coordinates which I am using are not appropriate to describe this region, but well, I'm not touching this issue. But if you use proper coordinates, everything is smooth, both at the ergosphere and actually on the horizon as well. So this is not a real singularity. So it's very smooth, and if, for example, you are brave enough and determined enough, and you plan to fall into a rotating black hole with the mass 10 to 9 solar masses, you will survive. I mean, till being crushed at the central singularity, but you will survive. Nothing will happen. The gravitational accelerations will be of order of the Earth's gravity when you cross the horizon. Only later it will become like spaghetti and whatever dramatic things. So this marginally stable orbit now depends on this black hole spin. When we consider co-rotating orbits, then it shrinks. And notice that we now change units. Now we are using gravitational radius, which is 0.5 of Schwarzschild radius. So that it shrinks from 6 to 1, or half of the gravitational radius. But if you consider counter-rotating orbits or then the marginally stable orbit is located farther away. So it depends on the location, and then you have to calculate the accretion efficiency separately for each value of the black hole spin, because it will depend on that. So for the Schwarzschild radius, as I told you, it's something like 5%, but for this maximally rotating black hole, it's something like 40%. So this is the highest really energy efficiency easily available. There are ongoing discussion whether we can still have higher efficiency if we play with magnetic field, something like that, but that's kind of tricky. But without tricks, this is the maximum, but it's quite a lot. If you can get 40% of the rest mass out during the accretion, that's really fantastic source of energy.
I have a question here.
Yes.
Like, in the retrograde motion, the particle will cross through the ergosphere, and it will.
No, I mean here this is only.
Let's consider there is a retrograde motion of the accretion disk, and there is some point.
It will be reversed. Just force will reverse it to co-rotate.
So the black hole spin always will be spin up.
Yes.
So there will be no chance of spinning down. Even the accretion disk is counter-rotating with the black hole spin.
Yes, in this way, yes. On the other hand, if you have this Penrose process, whatever, then you can extract the. You can.
Sorry, I didn't get the question, but I'm interested in it.
The question is, like, you have a black hole spin.
Okay.
The disk is rotating counter to the spin.
Yeah.
But according to the picture, you have the ergosphere. At some point, the material will start to rotate along the spin. So in this sense, you will always spin up the black hole.
No, because when finally, yes, the particle will be co-rotating, but the black hole has to do the work on the particle, right? So the net angular momentum is sort of conserved. So the effective A will decrease. So this is why, yes, in the case of mergers of two black holes, you expect high angular momentum spin of the resulting black hole because you have a lot of angular momentum in the orbit. But if you have accidental accretion episodes, small accreting things from various directions, then systematically you decrease the angular momentum. And then you decrease A.
Yeah, because actually the frame dragging, this dragging, it means that if I look from outside, someone who has zero angular momentum, but he's inside the black hole, this is moving still in the with the frequency of the dragging. So even if this matter is rotating in the same sense of the black hole, it can have negative angular momentum and so give a negative amount of angular momentum to the black hole. It's weird geometry stuff of general relativity.
So it was faster this time than I thought. Probably I was faster talking because of the cold and being a bit more tired. So you have homework to do to understand the instruction. Calculate the angular momentum on circular orbits in Shortcircuit metric, because I didn't do this part of the calculation. Discuss the problem of R equal 1.5 Shortcircuit radius and how this relates to a black hole shadow and silhouette. This is really an important exercise. If you have problems and if you don't do it properly, I will explain that later because it's closely related to the M87 image I showed you before. And then the second exercise, what is the Newtonian efficiency of accretion if we borrow a concept of ISCO from pseudo-Newtonian approach, but we use only Newtonian potential? So then you can compare all those approximations, because in published papers, many people use different efficiencies. Some people use Newtonian efficiency, but assuming ISCO, pseudo-Newtonian efficiency, Schwarzschild efficiency, 10% just in case, and then full GR, which really depends on black hole spin, and then you have to be specific, or you have to do some estimates of the rotation. Okay, so this is really all I wanted to say, but maybe there are still some questions. Or comments. So actually I could prepare it, even perhaps a bit more material, but well, I can tell you one more thing, which I did not really prepare for that, because I thought it would be too much, but finally it's not too much. This is what we did during this lecture. If I can go back. For example, using this pseudo-Newtonian prescription for the angular momentum. So if you have the prescription for angular momentum, of course you have also velocity in the direction of phi. You have full description of the motion. So that can be already tested in observations. If somebody of you works with X-ray data and K-alpha line, in the sense of, well, you probably use full GR to model K-alpha line, right?
I don't use like to model the K-alpha line. I mostly use like data from X and
So that you don't have K-alpha, strong K-alpha line there.
Yeah, mostly not.
But in AGNs or in galactic sources, there is frequently a strong iron line emission, which comes from the disk. And this iron line emission, if we assume that this iron is not highly ionized, so it's the emission photons are coming from the innermost iron orbit. So then the photon orbit always is, well, the emitted energy of the photon is always at 6.4 K. For every radius, the emitted energy is the same. On the other hand, because those photons come from all those different circular orbits, then you have to calculate additional effects, right? So you have to calculate the gravitational effect, you have to take into account the rotational velocity, which is related to this Keplerian rotation. And then from that, you have to calculate the radial part of this velocity. In the case of Newtonian physics, this is also simple. So then you will have a spread of photons. And this will give you the shape of the line. And this is what is determined observationally. So in this sense, from observations, reversing the problem and saying that in general, it's not just pseudo-Newtonian, but full GR Kerr metric case. From this shape of the line, you can estimate the angular momentum of the black hole. This is one of the ways to measure the black hole speed. The other method is based on the efficiency. Okay, but I decided that I will not talk about a lot about this K alpha line, because that means introducing, honestly, quite a number of physical statements, partialization of iron, all those orbits, whatever, and then I will talk about it later at some occasion.